Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's start. So this third lecture is about something that's a more general version of the Netflix problem that we talked about. It's called topic modeling. And we'll talk more about this next time as well. And today I'll just introduce a very special case of this. And the goal is to introduce you to a technique, which is a generalization of this, the spectral decomposition, which we saw last time. And this technique involves tensors and tensor algebra. And so this is, I think, a very nice technique, so I wanted you to see it. So that's the reason why I'm doing it today. Next time we'll have another take on this same problem, topic modeling, and we'll have a different technique, okay, which I think is also very important. Okay, so topic modeling arises in, let's say you're talking about documents. Okay, so you have a corpus of, so you're trying to uncover thematic or topical structure in a corpus of documents. Okay, there's a database of documents, and it's completely unsupervised. Nobody has labeled them or anything. And you're trying to just automatically uncover the topical structure that in this, so for instance, you might have the database of all articles in the Hindustan Times or the Deccan Chronicle from the last 30 years. And you'll run your algorithm on them, and you'll come up with a list of, say, 100 or 200 topics. And then you'll say, and you label for each of the documents, okay, this document is about topic 1, 7, and 20. Okay, and this other document is about this. So these 4 topics. Okay, because one document may be about multiple topics, right? It could be a combination of weather and sports or something, right? So that's the kind of, sorry? Is not known. That has to be uncovered as well. Yeah. It's completely unsupervised. Okay, so the set of topics is not known. So suggestions? What would topics correspond to? Yeah. Distribution of words. Okay, so you're already making one conceptual leap, which I should mention, which is the bag of words assumption. Where a document is equal to a vector of words. So documents obviously have a linguistic structure. There's paragraphs, and then within the sentence, the order is very important. And we're going to ignore all the order of the words, and we're just going to treat a document as a vector of word frequencies. Okay, this is a simplification. This is there's a leap of faith, what I call making up stuff, right? That somehow doing this still doesn't obscure the topical structure, which makes some kind of sense, right? In a document about politics, certain words will appear. And so even not knowing the order in which they appear you should be able to sort of tell by just looking at which words appear in the document what the topics are. Okay, so that's an assumption. So now you're saying a topic is a distribution on words. That makes sense, right? Topic is a distribution on words. Politics, the topic politics may have a different distribution than the topic sports. Okay? So assumptions. Topic is just is also a vector or distribution on words. Right, a vector of word frequencies is just a distribution, scaled. Right, a distribution is just a vector of word frequencies, P1, P2, so on. Pn, let's say n is the vocabulary size. And so sum of pi is 1. And pi's are non-negative. Okay, so that's a topic. All right, so then what's a document? How is a document generated? So we are again still in this phase, the first phase of making up stuff that I call, right, the process of making up things. That when you're doing machine learning, you have to make up a model, which is some kind of a story of how the data was generated. So how is a document generated? So given that so these topics are not known, okay? These are unknown. This is a latent variable. Latent variable. This is a very important concept in machine learning. It's a variable whose value is not revealed to you, is not in the data. Okay? A variable whose value is not directly visible. So our data is just the newspaper documents, namely the newspaper articles, and the latent variables are these topic vectors, the distributions, and these are latent because they are not visible to us. Okay, we're going to uncover them. Okay, so those are latent variables. So now how would the document be generated from these? So a document could be a distribution on topics. Yeah, which I sort of suggested earlier that a document could be about politics and sports. Okay, so a document could be, so generative model for document, generative model for a document is that you pick a distribution. Distribution on topics. Okay? So there's some stochastic process that'll pick a weighting of the topics. Okay? This document is going to be 1/3 about politics and 2/3 about sports. Okay? So 1/3 times politics, 2/3 times sports. Right? So there's some weighting of the topics. Now, let's think about it. So what does that imply? So mathematically, what does that mean? So there's some vector of frequencies corresponding to politics, and there's a vector of word frequencies corresponding to sports. And when you're generating a word in the document, So the document is over here. And I don't know, let's say okay, so you could have the word cricket, right? And it has a certain frequency in the document, right? Cricket may appear with pretty good probability in sports, at least if it's an Indian newspaper. So there's a certain probability here. And then it may occur with some maybe small probability in politics, right? And then probably there's Pakistan in that document too somewhere. But so now the word cricket appears in the document. So if your generating model is with 1/3 probability, you pick the politics distribution. With 2/3 probability, you pick the sports distribution, and you pick the word from there. So then the probability of picking the word cricket is 1/3 the probability that it appears in politics, and 2/3 the probability that it appears in sports. Okay, so this is what happens for a document that's 1/3 about politics and 2/3 about sports. Okay? And so we are assuming, so therefore, this document is exactly equal to 1/3 times politics plus 2/3 times sports. Okay? This distribution, the document distribution, is this. This is the document distribution. And then maybe the document actually only has 500 words. This is a distribution on the entire dictionary, 50,000 words or something. So maybe out of this distribution, you picked 500 words according to this distribution, independently. Okay? So maybe the document is equal to 50, or say 500 samples from this distribution. Okay? Yes?
So it's not the same as first selecting a topic and then generating 500 samples from that topic.
No. So you take this combination of these two distributions, you get a new distribution from which you are generating. Yeah. If you're going to generate only 500 samples. Yeah, you generate 500 samples from this new distribution. Now, obviously, if it's 1/3 and 2/3, then out of 500, about 1/3 of them will come from here, and 2/3 will be from here. But notice that the same word could occur in both, right? Like cricket might occur in both. So the probability of the word occurring here is yeah, that sum, that weighted sum. Okay. Here, these are distributions, so their sum is 1.
Individually one?
Yeah, individually. The sum of all these entries is 1, and this sum is 1. So therefore, notice, yeah, good point. So if you take any weighting of the topic vectors, there are, let's say, 100 topics, right? These are vectors that sum to 1. Then this will also be a vector that sums to 1. Okay, so that's the idea in topic model. So there's a model that there's some latent variables, namely the topic vectors, and then somebody went and probabilistically, generated documents as follows. For each document, pick a weighting according to some distribution of these topics. So you could also have ways of picking topics where you pick, say, 4 topics per document or something, up to 4 or something. And so you have some probabilistic process for picking a weighting of topics. Then you take this corresponding sums and then generate documents from there, say of size 500. Okay? Now you can see that This is a more general paradigm, right? That you could have similar topic models in all kinds of other settings, like genetics or all kinds of other things. Okay, so not just for texts. Okay, that you have some underlying latent variable, namely types, right? And then your type is some combination of the latent types. Okay? And indeed, this has been applied in all kinds of settings. But we are talking about text for just concreteness. Okay, so the topic modeling problem is, given the corpus, uncover the topic vectors or the topic vectors and the distribution used to generate the documents. Okay? And then some human expert might go and look at these topic vectors and say, yeah, that topic vector looks like politics, or that looks like sports, or whatever. Okay? So, actually, let's first criticize the model already. So, can you see ways in which this model is not quite realistic? Just staying with the newspaper article application. Yeah. Yeah.
We are assuming there is it's generated using some distribution over the topics.
Yes.
But there are many umpteen documents in the repository. So each document could have been generated using a different weighted distribution. So then
A different weights or different distribution?
there are different weights on the topics.
Yes, that's allowed. We're not saying it's always 1/3, 2/3. You know, there's a way of picking these numbers, which is also probabilistic.
Which is the distribution used to generate documents it is not weighted.
Right. So for any particular document, you may not be able to say it was used. You know, it was a 1/3, 2/3 weighting. You may have some kind of max likelihood kind of thing that most likely it's 1/3, 2/3.
So the problem is for each document you would like to generate
You may. So the first thing would be just to uncover what was the method used to pick for the entire corpus these weights. So the same method is being used. So for example, you know, here's a distribution, right? Pick a random set of at most 4 topics. So among all sets of up to 4, pick a random set of 4 topics and give them equal weights. Right? That's a distribution on the topics. And so that's what you have to uncover. Yes. That's the assumption, yeah. That's the assumption. That there's an underlying distribution like this of picking topic vectors, like this or something else, and that was used for the entire corpus.
Before you start working on this problem, you have to
a form for the distribution, right?
Some clear classification of clustering even before demand. Because if you take an arbitrary document corpus, this is some traditional party.
Right, so then people studied this and they've played with various distributions, and there are some popular types, like Dirichlet is a popular choice, is a family of distributions. So any other criticisms of this model?
Okay.
Yeah.
So one is that it's possible that that a document may be about a topic,
Yeah.
but it may not actually contain a lot of words from that. So it may contain some keywords. So like, for example, if the news article is that the Prime Minister met with an accident. Okay. So that will contain the Prime Minister and some very general things. It will not really contain a lot of Prime Minister related words. But still it's about the Prime Minister.
No, I don't, that's just saying that, if you're not taking a lot of, say there's a topic here called Prime Minister, and you're not taking a lot of words from the Prime Minister topic,
Yes.
then it has a low weighting.
Yes.
That's all you're saying. So that's allowed by the model. It's not, you can't say that your example doesn't fit in the model.
No, but the model will say that the weighting of the Prime Minister topic is low, but actually should be high.
So where are the other words coming from? What are the other words in the document?
So like there are some kind of medical words or hospital, those kinds of words.
So therefore it's also about medical something, right?
Yes.
So it's about Prime Minister and medical.
Yes.
And so maybe it's only 1/10 about the Prime Minister and 9/10 about medical, right? His medical condition after the accident.
Yes. But the critical topic here was the Prime Minister. So
That's a matter of judgment, right? If 9/10 of the words are about his medical condition, you can argue that it's 9/10 about medicine, right? Or medical condition or whatever. People being in hospitals, right? So that's the model allows for this, yeah.
Could it be that each kind of word that is present in a dictionary is modeled on a different kind of a distribution, and so when you try to fit it into say different categories for a document, it does not match. All those distributions do not match the distribution of the document itself. It's modeled on a different kind of a distribution. The document is modeled on a different kind of distribution, and not all the words in the dictionary are modeled on a similar kind of distribution.
So every word has its own kind of distribution. So maybe let me say if this, I sort of hinted at this already. So let's say the word cricket appears in politics, right? Let's say. Well, when cricket appears in politics, chances are Pakistan, for instance, appears a lot, right? Because that's where the politics arises, right? So there's correlations among the words. That if cricket appears in politics, Pakistan probably appears, right? So there's correlations. Whereas this thing is just saying that, in politics, the word Pakistan appears, right, with some probability, and cricket appears with some probability. And then, conditional on knowing that the cricket appeared already, Pakistan's probability has not changed. Whereas it does, right, in real life documents. So there could be correlations which are not allowed here. Yeah.
One criticism is like if you pick a writer and pretend that this is how you generate a document, they might take it as an insult, right?
Right. Other writers just monkeys typing randomly, right? Picking. So, so that in general, it's artificial intelligence, right? And then now we're doing machine learning, which is even a subcase of artificial intelligence. The model may not accurately reflect what a human person would do, right? So we're not trying to mimic human intelligence here or explain human intelligence. Yeah.
Second thing is a slightly more realistic situation is when if you want to figure out whether a document is about a particular topic, words that is generally found in the document. Usually written by a single person. This vocabulary is very unlikely to span this entire distribution of the topic. You would rather be focusing on.
Okay, so yeah, I think what you're saying is that the documents were written by different writers, and so when writer 1 writes about politics, they may have different distribution versus writer 2, and that's another kind of correlation, or hidden latent variable, which is not accounted for here. That's right. So so in general, latent variables, you can introduce additional latent variables in the model to account for those kinds of variations, which we're not doing here. Yeah. Any?
When you are trying to uncover the topic vectors, do we require them to be orthogonal or orthogonal?
They definitely will not be orthogonal because they are non-negative vectors. And non-negative vectors cannot be, I guess they could be orthogonal if they're disjoint, but otherwise, in general, they will not be orthogonal.
So in such a case, for a given document, we could have several linear combinations of topics.
Indeed. Indeed. Very much so. Yeah, this non-negativity is a big problem. Yes. Okay, all right. So I think we've discussed this model enough. Let's do something with it. So the simple case that we are going to do today is that a simple case that each document is about one topic. Okay, so you don't have these combinations. Each document is about one topic. So in this case, we'll do an algorithm, which is already fairly non-trivial, and then we'll discuss a more general case next time. Okay, so now let's step back a little bit and talk a little bit about how you uncover parameters of a distribution. So this is something called the method of moments. So for instance, if you know that the unknown distribution is a Gaussian, right? So if x is some n mu sigma square, and trying to figure out mu and sigma square from samples. Okay, so the univariate Gaussian here. So how do you recover mu? You compute E of x, right? The expectation of x. So you look at some samples, you compute E of x, and so this converges to mu if samples are independent. So if you draw independent samples from the distribution, this converges to the mean. And similarly, you can compute E of x minus E of x squared, right? The empirical variance. And that it's very close to sigma square. Okay, so you compute these moments, right? These are called moments. This is the first moment, this is the second moment, right? And this gives you information about the hidden variables, right? The latent variables, mu and sigma square. Now you can, let's take this one more step. So suppose in the univariate case, now let's say X is a mixture of Gaussians, two Gaussians. Two univariate Gaussians. And let's say with weight W1, it's the Gaussian n mu1 sigma 1 square. And with weight W2, it's n of mu2 sigma 2 square. Okay, so this is a case I mentioned earlier. For instance, heights in the population, and there's a female part of the population that's male, and those are two different Gaussians. So those are the weightings, W1 and W2. So now if you compute the first moment, okay, so the sample is with probability W1 generated according to this Gaussian and W2 generated according to that Gaussian. So what does it converge to, the sample mean? So it'll converge to W1 mu1 plus W2 mu2. And now what about the variance? Okay, so I computed the variance. It converges to, I think, what did I get? I think it's something like W1 sigma 1 square plus W2 sigma 2 square plus W1, the mu minus mu1 square, I think, where mu is this, okay, this is mu, plus W2 times mu minus mu2 square. I believe this is correct, okay, but maybe I made a calculation mistake, but I believe this is correct. So anyway, it doesn't matter, okay, so it converges to something. So do two moments suffice? No. Why? You have 4 unknowns, right? You have 6 unknowns, right? W1, mu1, sigma 1, W2, mu2, sigma 2. So 2 moments won't suffice, right? They're just 2 equations, right? You can't solve for the variables in it. So you need more information. So what's the next information you can compute from your sample? Third moment. And what's another piece of information you can need? Fourth moment, right? So you can keep doing this, right? So by staring at your sample and computing more things like the third moment, fourth moment, you get more equations, okay? And then at some point, indeed, you can verify that you can recover, there are sufficient equations to recover all the variables, okay? All right? And you know, how many moments do you need to recover the latent variables? This is not an easy question because we're talking about highly nonlinear systems. Okay, it's not just linear systems. Once you have n independent constraints and n variables, you can solve it, right, and get your variables. These are nonlinear equations. The issue of solvability is much more complicated. Solving nonlinear equations, I've mentioned before, is NP hard in general. So this is a much more hairy problem. And in fact, there are distributions, families of distributions, where you can compute any number of moments and you cannot recover all the parameters. Those distributions are called non-identifiable. So they're not identifiable from any number of moments. Okay, so that's a very simple introduction to the method of moments. So we will use the method of moments.
Is it because there are multiple choices of parameters that it produces the same distribution?
Same moments, yeah.
Only the same moments, but the distribution is
There are certainly even distributions where different parameters can produce the same distribution. That's right. Yeah.
So to know the values of these components, can we put additional constraints, say W1 plus W2 is equal to 1?
Yeah, we have that constraint too. That's right. That's allowed. Yeah, that's known. Yeah. Yeah. W1 plus W2? No, you throw in any conditions that are known. Yeah. Or from domain knowledge, you may know something. Yes. That the variance is this much or mean is this much. Yes. And you can throw those in. Yeah. Any additional constraints you throw in will only make your job easier. Okay, so let's compute the moments of this case. Okay, this case, where each document is about one topic. Let's compute the moments. So now, if each document is about one topic, what have you got? So there's some unknown topic vectors, V1. So these are topic vectors. V1, V2, etc. VT. And there's some weighting of these topic vectors, W1, W2, WT, where sum of WI is 1. So when the document is produced with probability W1, you pick this topic, and then you just use this topic to generate the document. And W2, you pick this one. Okay? That's the model. Yeah.
So, in the case of Gaussians, so
Oh, going back to this? Yeah. Sorry? How many moments? Homework. Okay. All right. So okay. So that's the model. That's the assumption, right? And so let's compute the moment. So the document you get is X, which is just samples from that distribution. Okay? That's the document you get. So what's the expectation of X? Just the summation, right? Summation Wi Vi. So that's the expectation of the variable, and if you do enough samples, it'll converge to that empirically. We've been talking about Chernoff bounds and so on. So this will converge to that very fast. Okay, now let's compute the second moment. Now the second moment is just, you're computing, let's see, so you're computing the expectation of xi, xj. Right, for all ij. Which, remember, we had this notation. This is just, so if you do this for all ij, that's like computing the moment, the expectation, of this matrix. X transpose. Okay, remember that this is X transpose. So the ijth coordinate is I, j. Okay, that's xi, xj. So you're computing the expectation of this matrix. That's the second moment. Okay, so using linear algebra allows us some brevity of notation. So what's that? It's a symmetric matrix, yes. Sorry? Yeah, but what is it? No, I mean, we don't know about spectral decomposition, but just in terms of the unknown variables, namely these vectors v1 through vt and the weights w1 through wt. What is the expression for this? Right. So you're saying that the expectation of xi xj will be, what's your guess? No. So it's going to be this. Summation, I is overloaded. W little t, V t, I have too many t's here, ij. That's expectation. Sorry? Oh, Vt is this little t. V sub little t. I'm sorry? They're distributions. Okay, a distribution is a vector. Yeah, V is a vector, yeah. So let me just stick with T here too instead of I. WT, VT. Okay, T is going to be my subscript for the vectors. Okay, because IJ is the entries. So this is just summation WT, VT, VT transpose. Because it's 0, 1.
I mean, VT is just the probability, right?
Yeah.
Is the expectation.
Yeah.
It's not true the expectation that X transpose is the expectation.
No, it is, right? So because each document is about only one topic.
Right.
We're studying that case. So when you pick X with probability W1, you pick this one, right? And then the contribution to the XIXJ would be just this times that.
Those are probabilities of which you make Xi 1, is it, or not? I mean, those are
Xi.
probabilities of right? X is a random variable.
Yes.
And once you pick the topic, it tells you the probability, but
Yes.
not the random variable itself.
Once you pick which random variable? I'm not following. Okay, so think of it this way. X transpose, right? So what were the events? You picked the first topic with probability W1, right? And then when you pick that topic, whether you pick Xi and Xj both is just depending upon, this vector, right? V1's ith coordinate and V1's jth coordinate. And then there's an event that you picked this topic, in which case the expectation of Xi Xj depends only on this entry and this entry.
But if you write it as a sum of vectors, then there are cross.
No, I'm taking the expectation of this vector, right? This vector, the empirical average, right? There's some times when with probability W1, right? W1 fraction of the times it's just this vector, right? With W2 probability it's this vector. W3 probability it's this vector. It's just exactly, I'm reading off with probability W1, let's look at it this way, right? With probability W1, this matrix is exactly VT transpose.
So I think I'm not understanding the model because VT is the expectation of XT, of X if you pick T, right? Now let's say
VT are the latent variables. V1 through VT are the latent variables. The topic distributions.
the vectors.
Yes.
And I mean, subject to that, what's the probability distribution of X itself?
So with probability W1, it's this. With probability W.
Once it's that, what does it mean? That means it's just something that doesn't work.
Yeah, you're just picking all the words from here.
Oh, you just pick all the words.
No, it's just a probability.
Well, it's Bernoulli or something, right? What is it?
Just IID samples from here. So just look at this, right? This vector, right? With W1 fraction of the time, it's just this vector. So XX transpose is just this times its transpose. With
The expectation of the
yeah. But we're just taking 500 samples from that same topic, so it'll be exactly that, or close to it. Anybody else? Yeah, ask a question. WI is the weighting. So with probability W1 you pick the first topic. With probability W2 you pick the second. But you pick exactly one topic for the document. Of the documents, yes. W1 fraction of documents of topic 1. You just know which one, yeah. Yeah.
So just to get this clear, so a priori you don't know what are the topics, what are the number of topics, what are the...
Let's say I know the number of topics for now,
Okay.
yeah. But it's not important, yeah.
And the assumption each document is about a single topic. And
Yes.
from that, we want to determine all these particles, W1.
That's right. That's right. Okay? Any other question? Yeah.
So here X is exactly what is X here? The document.
X is the document, yes.
So number of entries in X is the length of document. What is entries in X?
Okay. So you know, okay, so for simplicity, just assume that I'm given the entire distribution. I'm actually only given samples from that distribution, 500 samples. But let's say I'm just given the entire distribution.
Okay, so is it the document distribution?
That's it, yeah.
Okay.
Okay. The expectation will work out the same, yeah.
Because if you take 500 samples, then this won't. Then,
It may not converge enough. 500 is not enough, you're saying.
no. No. So that means the length of X will be 500, right?
The random X,
The length of X.
the length of X. No, so X, sorry, okay, so if it's of length 500, it's just a sparse vector. Okay, so it's zeros most of the places and ones in the places where you picked.
It's a frequency vector of the.
Okay, so for simplicity, just assume that I pick a topic, right, with probably W1. Just give me the entire vector. That's the document. Okay, forget the 500. Okay, the 500 is not going to matter because, you know, in the expectation it'll be the same. Yeah, there's a very tiny dependence or correlation because, you know, 500 is a fixed number, so there's a slight bit of, but it's not materially very different. So just assume that you're given the entire distribution. Okay. The problem is that that's not a very good setting because if you're just given the entire vector, then you just you'll see in your documents that there are t vectors, distinct vectors, and you just look at it. So that's why I'm saying 500. But for the expectation, just imagine that. Yeah.
The 500 was the one. You pick one.
One. Yeah.
The expectation of X is 0 because only one.
No, you need at least two.
Sorry?
You need at least two.
But what is the role of 500? I mean, there is a difference between 1 and 500.
There's no difference between 2 and 500.
If I pick 2 words,
Yeah.
yeah, yes.
How am I doing on time?
Oh, yeah.
Okay. Okay? Yeah.
And this expectation is the empirical expectation over the corpus.
Yes. Okay? Now, this may start reminding you of singular value decomposition, but big difference. What's the big difference? They're not orthogonal. Okay? These vectors are not orthogonal. These are distributions. They're non-negative. Okay? Now let's do the third moment. Okay, so we'll call this M1. This is M2. And this is M3. So So let's do the third moment, and I'll then introduce a notation, actually. So M3, the third moment. To express M3, we need a notation. Okay, so I'm going to introduce tensor notation. A tensor is just a high-dimensional matrix. Okay? So it's just so K tensor is just a K-dimensional matrix. Or matrix, or what do you call it? Array, okay? So a matrix has Aij. Now you may have, let's say if it's a 3 tensor, you might have Aijk entries. Okay, n by n by n. Okay? So now the third moments are expectations of xi, xj, xk, right? So the natural way to represent third moments is via a 3 tensor. Okay? Now, another notation. So we saw that V times V transpose is a matrix, right? Where the ijth entry is Vi times Vj. Right? This we saw last time, this notation. So I'm going to introduce another notation. So this is actually also, this is represented as this, V tensor 2. It's an outer product of V with itself. Okay, it's just a notation. That's the same as this. But now this you can generalize to 3 and 4 and higher things. So V tensor 3, so outer product with itself 3 times. Ijk is just Vi, Vj, Vk. Okay? So now we're ready to express this. It's the expectation of x tensor 3, which is equal to summation Wt Bt tensor 3. Yeah.
Even the 2 moments.
Yeah. So don't worry about it. Yeah. There's a little fix to it which we want. Okay. So all right. So now we know this information, and we want to recover W1, W2, and these V's. Any thoughts? First time, who's seeing tensor who's not seeing tensor for the first time? Physicists? What? Engineer? Do you study tensors in engineering, or physicists? I mean, where did you study tensors? Oh no, I was asking who's seeing. What was my question? Who is not see? Who is seeing tensors? Who has seen tensors before? Yes. A few. Physicists or what? Where did you see? Okay, yeah, physics. Okay. Okay, so let's do this. Now, the first step is going to be, and then we're almost done. So the main step will be a simple transformation that that ensures or that that ensures that VTs are orthogonal or orthonormal. Okay, so we'll do some kind of a transformation which will ensure that the VTs are orthonormal. Okay, the important thing will be here. We'll get orthonormality here. Okay? So what is this transformation? So let me first point out that a 3 tensor, so just as a 2 tensor, right, namely a matrix, which is just a bilinear transformation. Namely this, right, summation. So it maps x and y, which are vectors in Rn, to summation ij, aij, xi, yj. Okay? A 2 tensor, namely a matrix, is just a bilinear transformation. Okay? And so if we apply some kind of a rotation or linear transformation on the x's, that's like a transformation on A. Okay? So A of some matrix, let's say M is taken, B, A of B of x, y, right, is just a so let's see, I want to say is it a b of xy. I want to say this, no, ba maybe. I think it's b. Ba, something like that. Sorry? Yeah, something like that. Okay. I'll take your word for it, okay? I'm not good at fixing these things online. Something like that, okay? So there's a way to, in that applying a linear transformation on some of the coordinates is like applying some transformation on the matrix, okay? The same thing holds for the tensors, for the 3 tensor. So what we're going to do is, so the idea is that, so M2, so observation, M2 is it can be represented as W times W transpose. Now, this is in general true for the second moment, because this is positive semi-definite, and this is just a convex combination of positive semi-definite matrices, which is also positive semi-definite. Don't worry about it. If you don't know about positive semi-definite matrices, don't worry about it. Just stare at this, okay? Because this M2 is just V diag W V transpose, where diag of W is just a matrix with W1, W2, etc. on the diagonals and zeros everywhere else. And V is just the matrix whose columns are the VIs. Okay? So it's clear that this expression is exactly this. Okay? Because multiplying by a diagonal matrix just scales all the columns by W1. Or let's do it from here. And now you just take the outer product with this, and so you get exactly this expression. Right? And this is V diag W square root, which just means that you replace all these W's by square root times diag W square root V transpose. No, I want the other way. No, this is fine, yeah. Yeah. So we see that this can be represented as WW transpose. Now, this is what's called the Cholesky decomposition of a positive semi-definite matrix, this kind of representation. Unfortunately, it's not unique. Okay? So this we know how to compute. So if we know that W, we know, right, just from the model, that M2 is positive semi-definite. So we know that it can be represented like this. We can compute such a representation, WW transpose. Unfortunately, that's not unique. So you could do this, but you won't recover V and diag of W. Okay? This is a very standard algorithm in numerical linear algebra, the Cholesky decomposition. Okay? So this can be computed. Okay, so it can be computed efficiently, but it doesn't give us this because it's not unique. Questions? But we know that this is some other matrix, right? S transpose. Right? This is the one we actually want. And this is what we've got. So turns out that if WW transpose equals SS transpose, and W and S are full dimensional, then there exists a rotation R such that W equals R times S. So they only differ up to a rotation. By rotation, I mean an orthonormal matrix. Yeah.
So suppose if we are unique, the decomposition
Yeah.
is unique, then
Would be done.
what we would do is like we would normalize, since we know that VI is sum to 1, using that we can extract VI.
Yes, we'd be done. Yeah. So observation is, if somehow this was unique, which of course would mean that a lot of mathematics would get inverted and radically changed and simplified. But if this was unique, indeed, we'd be done. Okay, so now orthonormal matrix is just a matrix which is of the form R1, R2, Rn, where these are orthonormal. Okay, unit vectors and yeah, orthonormal. So now. This. So now we see that, therefore, W is equal to R times V diag W 1/2. Right? For some R. Okay? Okay, so now we're almost done. So let M3 prime be the tensor given by x, y, z get mapped to let me sign this. M3 prime of x, y, z is equal to M3 of W inverse x, W inverse y, W inverse z. So that's the definition. I claim that since you know W, you can compute M3 prime. Why? I realize most of you are seeing tensors for the first time, but it's not at all a tricky question. It's just follow from the definition, so think about it. If you know W and you know M3, you can compute this new tensor. Why? You just need the ijth entry, right? So compute. Oh, you were asking?
No, I was giving a hint.
You were giving a hint, I see. Right, so you know a tensor, right? I already said a tensor, you know, well, it's just a three-dimensional matrix, right? So you just need the ijth entry. So what's the ijth entry of this tensor? I'll write it up here, so Mij is, sorry, M3 prime. Oh, I don't want an addition, so I'll just write a 3 tensor, okay? I won't have the 3 here. So Mij is just M of EI, EJ, EK. right? So therefore, this is just M3 prime of EI, EJ, EK is what you need for all IJK, and you just substitute W inverse of EI, W inverse of EJ, W inverse of EK, and compute this product, or this expression. Okay, that's a single number. Remember that I erased it. M of x, y, z is just summation of ijk, mij, xi, xj, sorry, yj, zk. Right? That's the tensor is just a trilinear form. So, right? So that's all you need. So you just compute this for all ijk. So we conclude that we know this. Any questions? Yeah.
So can you do an analogy that if x, y, and z were say the basis vectors for a 3D coordinate system, then a transformation has been applied to the 3D coordinate system, and the coordinate system has been transformed.
Yeah.
That's all that we're doing.
That's all we're doing. Yeah. Yeah. We change the coordinate system according to W inverse. Except it's not a it's not a rotation. W inverse is not a rotation. It's a transformation, yeah. Okay, so now the claim is that M3 prime is just summation over I equals 1 to T of 1 over square root Wi Ri to the 3. Okay, and this is ensuring this now. Right? Because now you have an expression like this, but the vectors in question are orthonormal.
What are RI here?
Ri is this rotation.
There's only one R.
We don't know R yet. We don't know R. We only knew W. R is unknown. Okay? This R is this thing.
Are there many R's? There's only one R.
There's a single R, yeah. RIs are the columns of R. Yeah, sorry. RIs are the columns of R. Okay, so this claim is showing that this has happened. We now have a tensor which is like this, but these vectors are orthonormal. Yeah.
Whatever Cholesky factorization we did, this what gave us W and W transpose, right? And this was the actual diagonal V. So this R is something that the Cholesky factorization is supposed to determine.
Yeah.
And the entire empty mesh now only depends on what the behavior of the Cholesky factorization, and not, it looks to me as if it is not depending on the data that we started with.
No, so it does. So the question was, now somehow we are working with something that we got out of the Cholesky factorization, right? The Cholesky factorization. The point is that this R is connecting what we know, namely W, right, this Cholesky factor, and the unknown, namely V and diagonal of W. So R is sort of connecting those two things. That's right. So ultimately, when you want to, for instance, get V and this, you might, for instance, well, we'll get it more directly, but. So the point is, once you know the RIs, you know the Vs from this. Indeed, yeah. If your Cholesky factorization, depending on what your Cholesky factorization was, this unknown R is different, but that R is what links what you know to what you don't know. It's interesting. Okay, so why is this? It just follows from, substituting according to this. Because W inverse of V is just W inverse of V1, W inverse of V2, etc., right? Vt. And so I see. I think I wanted R to be here. Okay. R is this. Sorry. Okay. Same thing. It's R is the inverse of the R we're talking about. So now, when you move W inverse to the right, and you move diag of W to the left, right? So now we have W inverse V. This is equal to diag of W minus a half times R. Okay, and that's just so therefore W inverse of V1 is just 1 over square root W1 of R1, and so on. Okay, so now you just stare at this. So we are replacing Vt by R, the corresponding R, divided by Wt. And now there's a cube here. So you get W to the 3/2 in the denominator, and that's Wt over here, so it cancels and you get 1 over. Oh, I went from T to I, I'm sorry. Just to be consistent, this is T. This one, okay. So you understand this, right? W inverse. So this is just this, right? So now when you do this transformation, right? What are you doing? What is this? I should have pointed this out. So notice that this Vt tensor 3, right? This is a tensor, right? If you now apply this transformation, this change of, it's not change of basis, but whatever, this transformation on all the coordinates, right? On all the x, y, z. So V3 of W inverse of x, W inverse of y, W inverse of z is just like Vt W inverse, or whatever, W inverse Vt, I think. W inverse of Vt. 3 of x, y, z. Right? So this tensor is exactly this tensor. I realize you all seen tensors most of you have seen tensors for the first time. I'm not doing anything very fancy here. I mean, all I'm saying, I made this point earlier, right, when I erased it, but that if you apply a linear transformation on the first coordinate x, that's like this. It's just like pre-multiplying, whatever. So that's what it is. And that's all I'm doing here. So therefore, and this we see is exactly 1 over square root WT RT. Right? So therefore, this is tensor 3. Okay? So that's what I'm doing over here. So we did all this stuff, and we've ensured this. There's a simple transformation which ensures that VTs are orthonormal. And it suffices to recover these VTs, namely these RTs. Any questions?
So the exponent should be 3 by 2, right?
Right, so there's a 3 by 2 in the denominator. And remember, there was an exponent 1 over here. So the 1 cancels with 3 by 2, and you get half in the denominator. Okay, the question was, this is square root of WT, then there's an exponent of 3, so you get WT to the 3 halves. But then there's a WT already here, so you get square root of WT. Okay? And so now, I'll erase here. So given M3 prime, which we now know how to recover RTs. Okay, and then we are done. There's actually more than one way you can do it, and the method I'll describe to you is not numerically as nice. You wouldn't want to implement this, but at least you'll see the idea. Okay, the correct implementation, maybe if I have time, I'll say a little bit. So idea is this, you compute, so M3, so pick a random x. Maybe I shouldn't call it x. Pick random vector y in Rn, or unit vector. And now you compute the matrix M3 prime y and star star. So these are left unspecified, and you're just multiplying by a single vector. So in general, tensor, 3 tensor times vector is a 2 tensor, which is a matrix. Okay, just as matrix times vector is a vector. A vector is a 1 tensor, matrix is a 2 tensor, is a 3 tensor. So it's exactly the same way. So what is this? Let's see. This is exactly equal to summation from that 1 over square root Wt times Rt and y times Rt 2. I want to remind you that this is exactly RT transpose. This thing. Okay, it's a matrix. Now I claim that just realizing this, you should now be able to see what to do. So what's the next step? So you compute a unit vector y, compute this matrix, and now do what? The spectral decomposition we talked about, right? Because now these are orthonormal vectors, so therefore the spectral decomposition of this matrix, which we've computed, will exactly be this. Okay? Assuming that the eigenvalues are distinct, which they will be. The eigenvalues will be distinct because these inner products with high probability, these are continuous variables. So they'll never be the same. So the eigenvalues will all be distinct. Okay? So this is, remember there was a, so now, continuing this, so compute spectral decomposition of this matrix. Okay, so it gives for all t RT and RT in a product with y divided by WT squared. Not yet. The only thing I've used so far is that these eigenvalues are distinct. So that's unique, the decomposition. And that's it so far. Okay? Now the trouble is, of course, that we get this. So we want to recover the weight. But if you have RT and you have Y, you compute this, and now you get the weight. So that's it. So the only place I use the randomness is to ensure that with high probability, these are all distinct. And now when you try to turn it into a polynomial runtime and so on, and you're working with finite precision, you have the obvious things to worry about, to make sure that they're not, within precision, they are not the same, and so on. So you need a certain number of samples. Yeah?
Since the tensor is the fuse, you can actually say the first layer of it, where it's like taking y is to be 1, 0, 0, 0.
Yeah, the trouble is that I'm not guaranteed that the eigenvectors the eigenvalues would be distinct. Right? Spectral decomposition is not unique if there are two eigenvalues. An eigenvalue is multiplicity more than one. Okay. I'm out of time. I forgot to say, very important, attribution. This method for the single topic is due to a Microsoft team. Yay. 3 very, very interesting researchers, Anand Kumar, Sue, and Kakre. Sue and Kakre are at Microsoft New England. And this is from, I think, 11. Okay, so this problem was introduced in a paper by Raghavan, Tamaki, Vempala, and Papadmitru back in '97, this topic modeling problem. This was a theory paper. And they also introduced this simpler case of one topic per document. But even that, they were not able to solve. And then other people made more and more progress, and then finally, Anand Kumar, Su, and Kakare solved it. And the exposition I've given to you is from a more recent unpublished paper by Anand Kumar Ge. He's a student at Princeton, Su, and Kakare. That is on arXiv now, so you can look for it. And this tensor terminology is from this paper. And this paper also gives a more numerically stable algorithm to do all of this, which involves the notion of eigenvalues for tensors. So one thing I forgot to say is matrices we all know and love. Tensors, everything is harder. Even computing the rank of a tensor is NP hard. So this was a result of Hofstad, at least for 4 tensors. 3 tensors are still open. So even computing the rank is hard. So things like what's an eigenvalue and eigenvector, those are also difficult questions, okay? Even mathematically. What's the correct theory of eigenvalues and eigenvectors for tensors? So all of that stuff is a little bit harder for tensors. But because of tricks like this, you can get these very nice looking decompositions of tensors. So the tensors of interest here have these nice decompositions in terms of orthonormal vectors and outer products of orthonormal vectors, and that is a much simpler case to deal with. Okay, so that's what this paper points out, and then they point out that there's like half a dozen interesting problems of parameter estimation in hidden Markov models, learning mixtures of Gaussians, etc., which can be all solved by this tensor technique. Very similar idea. You look at the moment matrices, you do some kind of a transformation, which they call whitening, which was this multiplication by this W inverse, and then you get a tensor in this kind of form, and then you're in business. Okay, so I recommend this paper. Okay, so I'll stop there. Any questions? Yeah, the first moment, asymptotically doesn't have a lot of information. Most of the information is in the third moment, right? There's n cube amount of information, and first there's only one. And I guess the first must be somehow in the third too. That information must be in there. So.